The Coast Guard final report was released on August 5th, 2025. It was 335 pages long and had a great deal of information that helps explain why Stockton was so confident in both hulls that he built. In this video, I'm going to tell you the story about his complete confidence in the second hull and how and why Stockton came to this conclusion. The strength analysis he was presented was excellent. The MBI final report states it this way. In summary, the safety factors reported for the final Titan hull design were well above the required thresholds for aerospace applications, ensuring a high margin of safety under the anticipated operating conditions. In a previously released Part 1 video, I told the story about why Stockton had confidence in the build of his first hull, the one that cracked in the Bahamas. Stockton had even more confidence in the second hull, the one that imploded. He was told by carbon fiber engineers that this hull was ready for Titanic depths. When I review the basis for the engineers' conclusions and Stockton's decision-making, I think you will be shocked by the process. Stockton really thought the second hull was indestructible.
And he told us that it was basically indestructible.
The Coast Guard public hearings left unanswered questions about who helped OceanGate engineer the second hull. Phil Brooks was the only OceanGate engineer employed at the time the second hull was being built that testified publicly, but he was a software engineer. His testimony was very important and mentioned some interesting things about the time period of building the second hull, but his story alone never filled in all the blanks. He never even mentioned the main company Stockton had hired to do the computer analysis of the second hull, Kier Aerospace. I will tell you this, Kier was the Boeing of the second hull. I suspected Collier's involvement because in the MBI documents concerning strain gauge placement, there was a single image that had the Collier name on it, but that was it. It was the only clue. We had to wait for the 335-page MBI final report to learn about Collier's work. And then, the day after the final report was released, the Coast Guard released additional information, 1,430 pages of transcripts. These transcripts included some private Coast Guard interviews. A significant interview was with Dan Scoville, and information provided here allowed us to completely figure out the second hull story. Let's jump right into understanding the story of Collier and the second hull. Watch until the end to methodically see the poor engineering decisions laid out, and at the end of the video, Jeff Ostroff will comment on my Titan book. So no one from Collier testified publicly at the hearings, and the 1,430 pages of transcripts do not include an interview with a Collier representative. It's unclear if the Coast Guard spoke to Collier or if Collier just responded in writing to specific Coast Guard questions. I am sure that Collier was all lawyered up because they were intimately involved with the second hull and they had no maritime experience. Dan Scoville was made the director of engineering after Tony Nissen was fired, so Dan was the second director of engineering and involved with building the second hull for Stockton. In his private testimony, Dan states that he found out about Collier in a trade magazine because they advertised themselves as experts in carbon fiber finite element analysis. Later, he would also state that NASA had worked with Collier and had confidence in them. Dan and Stockton had to hire Collier to do the FEA calculations for the hull because there was no one at OceanGate who would have been able to run their hypersizer software if they bought the software product outright from Collier. Here's how Dan described it in his testimony transcript. So we did a finite element analysis on that. I don't have the skill set to do that. Neither does anyone at the company, at least not at this point. So we hired a third-party company to do that. So we called a company called Hypersizer. He meant Collier. Their software is called Hypersizer. I found them in a trade publication. They specialized in FEA for carbon fiber. So they sell this product. I called them up and said, hey, there's nobody here is going to run your software. This isn't our gig, you know. We're not going to be able to buy your software and run it because we're not going to be able to get in and get the result out because we don't know what we're doing. Even though Collier was an aerospace company, Dan states they responded like this. Would you guys please contract with us to run your own software for us and analyze our hull? They thought it was a cool idea. They liked a different thing to work on because, you know, they work aerospace. Here are the two requests for proposals and purchase orders from OceanGate for Collier to do the FEA with their hypersizer software. This is for the second hull, referred to here as Cyclops 3. Request for proposal for engineering services to be performed for OceanGate. On December 31st, 2019, OceanGate issued a purchase order for $33,000 to Collier Aerospace. On May 29th, 2020, OceanGate issued a purchase order to Collier Aerospace for $37,500. I want to interject an interesting aside here. During the same time period, in the early 2020 time period, for some reason, OceanGate was simultaneously reaching out to Boeing again, but Boeing ignored them. Listen to Mark Nagley.
I think the last time Boeing was in discussion with OceanGate was March of 2020, where we declined to respond to a request for proposal.
I have a feeling Boeing did not want to deal with OceanGate and Stockton any longer. Now it's time to go through the MBI final report and review the collaboration between Collier and OceanGate. Again, we don't know exactly how Collier provided the information to the Coast Guard, but this is the content in the MBI final report. In terms of engineering this mission-critical structure, the carbon fiber hull, the information is shocking. As I go through these entries, try to understand how Collier, a professional engineering company, felt they were in a position to draft an engineering conclusion about the predicted strength of the hull and present it to OceanGate. And from OceanGate's perspective, how could they possibly trust the analysis? Because with an analysis such as this, you must have good data input to get reliable data output. You will see what I mean soon. The scope of their work was limited to static stress analysis, did not extend to fatigue, damage propagation, crack growth, or dynamic loading, which were outside the services Collier provided. According to Collier, the CAD model used for the analysis was created prior to the contract and provided by OceanGate based on previous work completed by Boeing. So all the work was static, nothing dynamic, and OceanGate passed to them some of the work done by Boeing, which must have been information from the 2013 feasibility study. The emphasis on static analysis is repeated. The first contract included an FEA with both 2D and 3D models. This included evaluating the deformation of the vehicle under static loads, analyzing the interfaces between carbon fiber and titanium, and determining the theoretical performance envelope of the pressure hull. Collier did do something smart. They knew they had to have metal domes to test the scale model hulls because during the Spencer scale model tests, the carbon fiber domes always failed. For the 1/3 scale tests, Collier designed a steel ring fixture to mimic the deformation profile of a titanium end dome. After the first 1/3 scale model test, Collier analyzed the failure load and measured wrinkles, attempting to adjust the finite element model stiffness to match the observed failure load. But concentrate on this next part, because here starts the failure to fully evaluate the test hulls. However, even after adjustments, the FEM was unable to predict the failure load in the second test due to the magnitude of wrinkles in the carbon fiber layers. Collier recommended that a high-fidelity damage progression model would be needed, a service their company did not offer. So the wrinkles were so bad on the first scale model test hull, they could not adjust the computer model for the second test hull predictions. They recommended a better modeling method, and it seems that OceanGate did not pursue it. So it basically means that the test models were not giving useful data to be extrapolated to the full-scale hull computer modeling. Furthermore, the test models were fabricated with a single layer and cure technique, so they did not match the fabrication technique of the full-sized hull.
We built 2 of them. The issue on those 2, they were not multi-cure, they were just single cure. And I can't remember the exact depth, but it was probably around 2,800 meters.
And both test models failed at about 2,800 meters because they would fail at the wrinkle. This was a weak area. So basically, the 1/3 scale test data was worthless. Dan Scoville did not think they would get to the Titanic if they could not fix the wrinkle problem. So basically, the bottom line was, are we going to do multi-cure or not? And so my mindset was, we're never going to the Titanic because we know this thing is going to get a wrinkle. We know that if it gets a wrinkle, it's going to fail based on all the other testing we've done, all the 3rd scale models we have made. We know that the hull will fail at, low depth, not making depth, right? Collier did help OceanGate with preparing for the deep ocean test facility regarding strain gauge placement for the testing. And this is why there was this one Collier image in the early MBI documents. It had to do with strain analysis of the titanium dome. And this was the plan for strain gauge placement. During DOF testing, there were 2 on the dome. But even when working on the titanium dome analysis and Collier trying to do a proper job for OceanGate, OceanGate showed their incompetence. For the full-scale test, Collier contributed by advising on strain gauge placement in the dome. Collier subsequently reviewed strain gauge data collected during the test, observing good correlation in trends with the analysis model. However, they could not compare absolute strain values because OceanGate did not provide the necessary gauge factor for the strain gauges. I can't fully explain the strain gauge controversy based on this paragraph, but various makes and models of strain gauges made of different materials have what is called a gauge factor, and you need to know exactly the model you are using to fully evaluate the data it is giving you. There was documentation for the model of strain gauge they were using, so this information should have been available. But apparently, OceanGate could not provide Collier with exactly what they wanted, so the conclusion was this. However, Collier was able to inform OceanGate that the relative magnitude between gauges was comparable to the model. So this is another example of poor attention to detail. They just accepted strain gauge assumptions for the domes that was less data than what would have provided a full picture of strain. This is an interesting entry. Since the contract was hourly based, Collier only performed tasks that were explicitly requested by OceanGate. This ensured that the scope of work remained focused and aligned with the client's needs and objectives throughout the duration of the project. The contract was hourly based. I believe this paragraph is code for the fact that OceanGate had a strict budget and did not want to pay for anything extra. Collier responded to a question from the Coast Guard about cycle life for the hull. In response to a question asking Collier if they had modeled fatigue for the new Titan hull in order to determine how many deep-sea dives would be possible before failure, Collier provided the following written response. Not by Collier. Our company does not have expertise in this area. When we asked OceanGate about this topic, we were told that their acoustic monitoring system would be used to detect damage growth in real time, and that this capability had been demonstrated on the previous iteration of the carbon fiber hull. This is another miss on a crucial point. OceanGate had no prediction on how many dives the hull would tolerate. Regarding the manufacturing, again, OceanGate handcuffed Collier because they could not provide good data. Collier was unable to model manufacturing process defects or knockdown factors for the full-scale Titan due to a lack of essential data from OceanGate. Knockdown factors are strength reduction factors that need to be considered in the modeling. Boeing emphasized this in the feasibility study from 2013. You can't proceed with modeling if you can't factor these in. Mark Negley had a classic line about this, considering the effects of defects.
We did a feasibility study, basically a concept or a trade study output, and didn't consider effects of defects or anything, that would have been in a detailed configuration and analysis.
Early in the project, Collier recommended testing with thick coupons, 1 to 1.5 inches, to derive accurate material strength allowables. But OceanGate later stated that such testing was not feasible due to the high cost of the required test facilities. Just as Tony Nissen, Boeing, and NASA had told OceanGate, the proper way to understand the strength of the final hull is to fabricate test coupons, which represent exactly the fabrication process, to know the final strength of the fabrication compared to the predicted strength. This paragraph used the term allowables regarding the carbon fiber system. Not having a materials expert on staff at OceanGate was a huge mistake. Dan Scoville, who was the director of engineering at the time and was responsible for communicating and coordinating the fabrication of the hull by Collier, Electro Impact, and Janicki. But he was an electrical engineer, not a materials engineer. This is what he told the MBI. They had to create sheets called the allowable sheets. The hypersizer guy asked us was, what are the allowables? I'm scratching my head like, what's that mean? And so then he explained it to me. Again, it's a little bit outside my area. I don't think it's the data sheet for just the carbon fiber. I don't think it's the data sheet for the resin. I think it's like the combination. Highly technical stuff if you're not in the industry, or you're maybe a material science guy, you might be struggling. As an electrical engineer, I was struggling with that stuff, right? So anyways, we were able to get the allowable sheet from somewhere because Boeing or somebody had used that material. Boeing spends hundreds of thousands of dollars to get this allowable. It goes through testing to figure this out. They don't necessarily just want to hand it to all their competitors, right? But somehow we had the allowable sheet for this Toray material we used. That's how we tried to get the correct numbers, the numbers we're looking for. We found it in the allowable sheet. And there's a Class A allowables and a Class B allowables, I don't know when you get to use which one, but depending on what aerospace thing you're doing. This admission by Dan is interesting. Stockton put Dan in a bad position. He did not have enough experience to provide constructive input on the carbon fiber processes in this hull. It's clear that OceanGate needed a materials expert on staff. Sure, they got allowables numbers from Boeing for the Toray product laminate, but who evaluated that in the context of the 5-layer co-bonded hull? We don't know. This is another example of a variable in the design process which adds to the question about the final strength predictions. These next paragraphs discuss how problematic this was. Since manufacturing defects are typically accounted for by modifying material strength, and Collier was not contracted to derive material properties for the final Titan hull, the company did not offer this service. OceanGate did not provide the necessary material strength data, nor was relevant publicly available data accessible for 5-inch thick laminate structures. When the issue of manufacturing defects was raised, OceanGate indicated that it would be addressed during full-scale testing of the hull. During 1/3 scale testing, Collier was asked to account for wrinkles by modifying the hole's structural stiffness in those areas. However, this approach was found to be unviable during further testing and was not applied to the full-scale Titan. The 1/3 scale test also did not provide sufficient data to estimate manufacturing process knockdown factors for the full-scale hull. Collier needed two critical pieces of information to estimate manufacturing knockdown factors for the Titan: the strength reduction as a function of defect magnitude and the actual magnitude of the defects on the full-sized hull. So, did Collier have the first piece of critical information? The 1/3 scale holes, which had large defects such as wrinkles, were unrepresentative of the full-scale design due to the differences in size and manufacturing processes, and therefore could not provide useful conclusions about how defects would affect the full-sized hull. Did Collier have the second piece of critical information? Additionally, OceanGate did not provide data on the magnitude of defects for the full-size hull, and measurements would have required non-destructive inspection or dissecting the hull, both of which were deemed unfeasible by OceanGate. So after all these problems with proper data input and modeling and the hull strength predictions, OceanGate just blew off the problems. They assumed the hull was strong enough and they could rely on real-time monitoring. OceanGate decided that the strength of the hull would be sufficiently validated through testing and real-time monitoring with acoustic sensors. OceanGate was confident that the RTM approach would be viable for assessing structural health on the final Titan hull well ahead of a catastrophic failure. But really, the worst part of this story is this. After all these inconsistencies with the modeling process, amazingly, Collier proceeded to give OceanGate an assessment of the safety of the hull. Let's quickly review the factors contributing to potentially poor computer modeling and hull strength predictions with the OceanGate and Collier collaboration. Only static stress analysis was done. The scale models gave worthless data. There was strain gauge specification confusion. Hull cycle life, or number of dives, was never predicted. Knockdown factors were unclear. No coupon testing was done to validate fabricated material strength. No non-destructive inspection was done to evaluate defects in the fabrication. No engineer of record for the co-bonding process. Accepting real-time monitoring data during actual dives for validation versus valid engineering before building the hull, no engineer of record for grinding down wrinkles, which we will discuss next. Based on this problem list, wouldn't you think that Collier would have backed off and told Stockton we have such poor data that our modeling is not reliable and we can't rate the hull? But no. They gave the hull a fantastic rating. This is how they did it. This is what they reported to Stockton. There are a few ways engineers work with margin of safety and factor of safety, but for this discussion, what they reported to Stockton to consider was a margin of safety and a factor of safety greater than 1. The safety factor, as was determined by Collier, of the Titan design was reported to OceanGate in terms of margin of safety and factor of safety. A positive MS, or a factor of safety greater than 1, indicates the structure is not expected to fail under the applied load. The analysis used composite material properties specified by OceanGate for the T800/3900 system, with classical aerospace methods employed to check stress and strain in the laminate. For the carbon fiber hull's material strength, the FS at 4,500 meters of seawater was reported with an additional 1.25 factor applied. In the axial direction, the FS was 8.2 and the MS was 7.2 in the general area, and the FS was 4.6 and the MS was 3.6 near a stress concentration at the titanium fitting. In the hoop direction, the FS was 6.6 and the MS was 5.6 in the acreage, and the FS was 6.0 and the MS was 5.0 near the titanium fitting. These values far exceed the typical FS requirements for commercial aviation, which is an FS greater than 1.5, and space launch, which is an FS greater than 1.4. For buckling of the carbon hull, the FS was 5.6. To put this in context, space launch customers such as NASA typically require an FS of at least 2.15 for buckling in cylindrical structures. So those numbers are more than great. They are amazing. But based on what we know about the process of arriving at these numbers, how can they be trusted? So it was Collier who gave Stockton great confidence in the second hull. In summary, the safety factors reported for the final Titan hull design were well above the required thresholds for aerospace applications, ensuring a high margin of safety under the anticipated operating conditions. This is why Stockton thought the second hull was indestructible, quote, a high margin of safety under the anticipated operating conditions, unquote, meaning this structure, used as a hull, could withstand 380 atmospheres of pressure. But Stockton did not want to pay Collier to dig deeper and analyze more. As was typical for Collier projects, Collier offered to conduct a deeper investigation and comparison between the test results and the analysis to help pinpoint all possible differences. OceanGate turned down Collier's offer and informed Collier that they were going to proceed with construction of the remainder of the final Titan hull. Dan's private testimony adds great information to what Phil Brooks said in his testimony about working with electro-impact.
When it came time to do the full-scale hull, Stockton did not want to do the multi-cure, and I believe that EI said that they would not build it. They would not build it without doing a multi-cure. That we had to do it that way or take it someplace else.
Electro-impact wanted to prevent wrinkles and strongly suggested a co-bonding technique with 1-inch thick layers. So, at no charge to OceanGate, Electro-impact built 2 test structures on the full-diameter mandrel. For one, they did about a 2-foot length of full-diameter hull, but just 2 layers, individually cured to test the peel-ply process between layers. We did, I believe, a full diameter, full thickness called a slice. So these were not full length, but one of them was like 2 feet plus 2 layers. That was to test the shield ply layer that goes between the 2 layers that get cured separately. Electro-impact was so insistent that we needed to do multiple cures. They paid for that themselves. They were so insistent. You're not going to get a good hull. You've got to do these multiple cures. Stockton kept saying no. Electro-impact then did a second test. They did about a 2-foot length of a full diameter hull with 4 or 5 layers to prove the co-bonding concept. And then we did a full thickness, but again, only probably 2 feet long, 4 or 5 inches thick, I believe, test part. Dan was impressed with the results because with these short segment tests, they were seeing the best results ever in terms of no wrinkles. But of course, it's always a challenge dealing with Stockton, and Dan tells an interesting story about how he proceeded with the full-scale hull and the 5-layer co-bonding technique. I thought there was no chance we'd make it to the Titanic, but since Stockton never stopped me, I continued forward. I got the first layer cured. I don't remember what the discussion was, but he didn't totally freak out at me, you know? It was kind of like, okay, well, whatever, and maybe we'll do more. Then the second layer, he didn't tell me no, got it cured. I think this went through the 3rd layer. Then he said, we'll just cure the final 2 inches all at once. I was like, why? You're so close. You've spent 80% of the money. Just do it. We were able to cure every inch, and we had a hole that we thought was, that was the first point I was like, okay, this might happen, right? However, Dan conveniently leaves out one of the most controversial things about the second hull that he was involved in, about sanding down wrinkles and high spots on each of the 4 layers of the co-bonded hull. So the layers must not have been perfect. Phil Brooks gave a lot of details about this during his testimony.
So when we started doing the multi-cure, what was done was they would do the first layer and then cure it, and then we had a group of people with sanders and built a tent, and they had to dress in very protective gear because the carbon fibers is dangerous to breathe. And they would sand down any imperfections, any sort of blisters or anything like that, and smooth it out as best they could. I know that Dan Scoville basically had come up with this method to do this, and it was done at every multi-cure layer.
And how would they remove these imperfections?
Just by sanding.
By sanding down on the carbon fiber?
Sanding down the carbon fiber, yes. I'm not sure what type of, it was obviously a power sander, but they would go over the whole thing and sand it down.
Sanding down the carbon fiber layer with dozens of sanding spots per layer and possibly hundreds over all 4 layers is not routine.
Would it be common practice to sand or grind those off to make the surface level for the next layer that will be put on?
No, that is not common practice. So you're removing material, you're making a discontinuity.
Or would you recommend sanding down wrinkles to smooth out the layer for the next layer?
You know, we would have looked at that, we would have characterized it, and then we would have done an analysis of the reduced performance.
Look at this picture of the outside of the finished hull. They did not sand this layer because it is the last layer, but every one of these bumps is an example of what they would have sanded away on layers 1 through 4. Don Kramer from the NTSB examined the cutoff ends, which amounts to about 8 inches of hull, and found 1 grind spot on the first layer, about 8 on the second layer, about 14 on the third layer, and 24 on the fourth layer. Kramer saw grind spots where up to 12 plies were removed, since each 1-inch layer is 133 plies. If 12 plies are removed, that is removing about 9% of the thickness of that layer at that spot. Who exactly from Collier, Electro Impact, or Janicki said this idea was acceptable? There is no information from Collier that accounted for this disruption to the laminate layers in their modeling. Since OceanGate did not do destructive testing, they had no idea what the porosity of the laminate was. Kramer tested the cutoff ends and found an average porosity of 2.6%, which is 5.7 times greater than the Torre specification. Who signed off on the final prediction of strength of the hull without understanding how much porosity was present in the 1-inch layers? In pieces of the wreck recovered from the ocean floor, Kramer found that the adhesive film between the layers was not 100% adhered, and even worse, there was evidence that it was breaking down. Who signed off on a final prediction of the strength of the hull without understanding the strength of the film adhesive bond? So Stockton thought the hull was indestructible because the engineers on the project were working down to the level of OceanGate and not forcing OceanGate to work up to the level of solid engineering. The hull actually performed well up to the end of dive 80 when the big bang was heard and the strain gauges showed an abrupt change in strain. If Stockton had used the worrisome data from his real-time monitoring system that he was so proud of and stopped diving after dive 80, we would be having a completely different discussion, and Stockton would have been remembered as the innovator he wanted to be remembered by. If you have enjoyed this content about the decisions made by OceanGate, the mindset of Stockton, and the detailed hull engineering explanations, then you should consider getting my book. I will let YouTuber Jeff Ostroff, another Titan disaster expert, tell you about the book. Links to the book and my other Titan YouTube videos are in the description. Please consider subscribing, and thank you for your time.
Oh, and by the way, I highly suggest you pick yourself up a copy of this nice paperback book here. This is called Titan, To the Titanic and Back, 13 and a half times by Gordon Telepon. And what I really like about this book, it has everything you could ever possibly want to know about the Titan, from the history of the company all the way to the end, to the last day of the implosion. And this is about 300 pages. You can also get the Kindle version and download that. And you can also get a PDF version, which is really cool because you can search. So this right here will save you from having to sift through hundreds and hundreds of hours of videos all over the web, because all of the answers and all of the key points that you need to know about this entire engineering disaster is right here in the book, including all of the mistakes made during the manufacturing of the OceanGate Titan submersible carbon fiber hull. And what I find especially useful is these key talking points that witnesses made during the Marine Board investigation there, and it's got the timestamps from the videos too. So you can go directly to the U.S. Coast Guard's live streams from the Marine Board investigation, and you could directly find those timestamps in there and listen to the conversations that were had.